Hello friends, welcome to the instruction set of 8085 microprocessor. I Sumant Kadwane and I shall be explaining you all the instructions of microprocessor 8085. The outcome of this video lecture is after attending this particular lecture you will be able to understand 8085 instructions. So in general, 8085 instruction or in general a instruction is a binary bit pattern that is designed inside a microprocessor to perform a specific task or any specific function. The group of these instructions is called instruction set. 8085 has 246 instructions and each of these instruction is associated with an operating code, that is opcode, and its operands. These instructions are broadly classified into five categories: data transfer instructions, arithmetic instructions, logical instructions, branching instructions, and control instructions. Let us see each one of these and let us start understanding the syntax and description of each of the instruction. So first group starts with the instruction data transfer instruction, that is nothing but copy and paste instruction. The instruction format for this particular instruction is opcode and operands. Basically, first we specify the destination, thereafter we specify the source. So basically the data moves from source to destination. First command is move. Move, that is copy the contents from source to destination. Remember, destination is specified in the first position and source is specified in the second position as per Intel format. So move rd comma rs, it will copy the contents of the source register into destination register. The contents of the source register will not be destroyed, but the contents of the destination register will be overwritten. The original or old contents of the destination register will be lost. Similarly, move m comma rs, it will copy the contents of source register r into the memory location. Similarly, move m comma rd, it will copy the contents of the memory location to destination register. Here memory location m refers to the address specified in HL register pair. For example, move b comma c, it will copy the contents of the register c into b. Move b comma m, whatever are the contents of HL register pair corresponding to that particular location, whatever are the contents, they will be copied into register. Next is mvi, move immediate 8-bit data. So here immediate 8-bit data is specified and that particular data is a 8-bit data. So it will move the immediate 8-bit data into the destination register RD. For example, MVI B, 57. The 57H will be copied into register B. Similarly, move M, data. So here it will copy the contents, whatever immediate data 57 into the M. Here once again M refers, whenever we are referring to M, it is nothing but the location contents of the memory whose location is specified in HL register pair or whose address is specified in HL register pair. Next is load accumulator. So this particular instruction will load the contents of the accumulator from the address that is directly specified. For example, LDA2034. Here it will copy the contents of the memory location specified by the address 2030-2034 onto accumulator. LDAX register pair, either BC or DE. It will load the contents of accumulator. So LDA stands for load accumulator and X stands for register pair. Here, for example, if LDAX B, so B stands for register pair BC. What LXI register pair, 16-bit data. It will load the contents of the immediate register pair with the specified immediate data into the specified register pair. For example, LXIH, 2034. This will load the contents of register pair HL with 2034. Here 34 will be copied into L and 20 will be copied into H. This particular instruction is used for initializing the address of the memory, which then will be used for example, in move B, M sort of command. LHLD 16-bit address. Load HL direct So what this command will do, it will copy the contents of 16-bit address into the register L. It will increment the memory and it will copy the next memory location into register H. So once again, a lower to lower and higher to higher rule will be followed. So it will basically copy 2 bytes of memory and it will load it into the HL register pair. STA 16-bit address. It will store the contents of the accumulator. So whenever we want to store the contents of the accumulator to memory, the memory location address is specified. The instruction is STA2500H. Next instruction is STAX and register pair is mentioned to you. So STA stands for store accumulator, X stands for register pair. So whatever are the contents of the accumulator, it will be stored not into the given address but for the register pair BC in this particular case, and in this particular register pair BC, whatever is the address, the accumulator will copy the memory location. Next instruction is SHLD 16-bit address. So in this particular case, the contents of register L are stored in memory locations specified by the 16-bit address, and the contents of the register H are stored into the next memory location specified. For example, SHLD2550. So the contents of the address 255 contents of this register pair L will be stored into the address 2550, and the contents of H will be stored in 2551. So once again, the rule that is followed is lower byte to lower address and higher byte to the higher. Exchange XCHG. This instruction will exchange the contents of register pair DE with the contents of register L. So lower to lower, that is the contents of L will be exchanged with the contents of E, and contents of H will be exchanged with the contents of D. SPHL. There is no operand once again, and it will copy the contents of HL register pair to the stack pointer. So once again, the contents of L will be copied into the lower order byte of the stack pointer, and the contents of the H into the higher order stack pointer. Remember, stack pointer is a 16-bit register, that is, it contains 2 byte information. XTHL. This instruction will exchange the HL register pair with the top of the stack. What it means, the contents of L register are exchanged with the location pointed out by the contents of the SP, and the contents of H register are exchanged with the next location, that is SP plus 1. This instruction is PCHL. It will load the program counter with HL register content. So whatever are the contents of the HL register, they will copy it into program. Next instruction is push register pair. It will push the register pair onto the stack. The register pair, it could be register pair BC, DE, HL or PSW, that is program status word, which consists of higher byte as an accumulator and lower byte as a flag register. So let us understand what this instruction will do. It will first copy the contents of the register pair onto the stack. How it does is SP is decremented and contents of higher order register, that is either B, D, H or A, are copied into stack, and thereafter further the SP is again decremented and the contents of the lower order register, that is C, E, L or flag register, are copied onto the stack. For example, push B instruction will first decrement the stack pointer and it will copy the contents of the B onto the stack. Thereafter it will further decrement the stack pointer and it will copy the contents of the register C onto the stack. So in this process, the stack pointer is decremented by 2. Next instruction is the pop instruction. The pop instruction will pop up the stack to the register pair. Okay, so register pair once again is the same what was applicable in case of push instruction. Here in this particular case, the contents of the top of the stack are copied into the register pair. The contents of the location pointed by stack pointer are copied to the lower order register. Stack pointer is incremented and the contents of the location are copied to the higher order register. And once again the stack pointer is incremented. So in this case, with the execution of pop instruction, the stack pointer is incremented by 2, and here it is a post increment operation. In case of push register pair, it was the pre decrement operator. For example, pop h, this particular instruction, it will copy the contents of the location pointed by stack pointer onto the lower order register, that is nothing but L in this case, and once again it will increment the stack pointer and it will copy the contents to the higher order register, that is nothing but H in this particular case, and once again it will increment the stack pointer. Out 8-bit port address, it will copy the contents of the accumulator to the port with 8-bit address. So in this particular case, port address is always 1 byte, that is nothing but, for example, 78H. So whatever are the contents of the accumulator, if we write the out 78, accumulator contents will be port address. In 8CH, for example, so once again 8C is nothing but the port address. So whatever are the data available across the port with the address 8C, it will be copied to the. Before we move for the arithmetic instruction, the summary of data transfer instruction is in front of you, one particular slide. So it contains all the move instructions, load instructions, store instructions, exchange instructions, and thereafter in-end instructions. Let us move arithmetic instructions. These instructions for operations like addition, subtraction, increment and decrement. In case of 8085, we cannot directly add or subtract the contents of the two register, but we can add the contents of the accumulator with the other register. Similarly, we can subtract the contents of one register from the accumulator, and we can increment or decrement the register or register pair or a particular memory address. So let us see the first instruction, add R. So add R or add M, it will add the register or memory contents to the accumulator. For example, add B, it will add the contents of the accumulator with the register pair, with the contents of the register B, and the result will be stored in the accumulator. The original contents of the register B will remain unaffected, and the final added contents of accumulator with register B will be stored in the accumulator. Similarly, add M will add the contents of the memory to the accumulator. ADC, add register or memory with carry. Okay, so it will add the contents. For example, ADC B, it will add the contents of the register pair B along with carry to the accumulator. ADCM, it will add the contents of the particular memory location along with carry to the accumulator. ADI 8-bit data. In this case, immediate 8-bit data is specified and it will add the contents of the immediate data to the accumulator. For example, ADI 45. So if accumulator contains 5, and if you use the instruction ADI 45, in that particular case, accumulator will hold 50H after the execution. ACI 8-bit data. I here stands for immediate data, and add immediate to accumulator with carry. So it is just adding the immediate data along with carry to the accumulator. For example, ACI 45H, it will see whatever are the contents of the carry flag, it will add it. It will add to 45 and same it will be added to the. Next instruction is DAD RP. So this register pair, it could be HL or D register pair, and it will add the contents to HL. So what this, in this particular case, HL register pair is acting as the accumulator. So whatever is the register pair, that register pair content will be added to HL register pair, and result will be stored in the HL register pair itself. Sub R, it will subtract the register content from the accumulator, result will be stored in the accumulator. Similarly, SUBM, it will subtract the contents of the memory location from the accumulator, result will be stored in the accumulator. These instructions are same as that of add. In this way, SBB, subtract the register contents from the accumulator with borrow, or SBBM means subtract the memory contents along with borrow from the SUI, subtract immediate data from the SBI, subtract immediate data from the accumulator with borrow. INR, increment register or memory by 1. So this instruction will increment the contents of the register or the memory location. INXR, here X stands for register pair. So whatever are the contents of the register pair, for example INXH, HL register pair contents will be incremented by 1. For example, HL register pair holds 2000. After INX H, the contents will be 2001H. Next is DCRR. It will decrement the register or memory contents by DCXR. It will decrement the contents of the register pair by. So this is the summary of the arithmetic instructions. Arithmetic instruction, it constitutes of addition, subtraction, increment and decrement that are shown in front. You can go through it. Next category of instructions is the logical instructions. These instructions perform the logical operations on the data stored in the register, memory and status flag. There are a number of logical operations. It could be AND, OR, XOR, rotate, compare or complement. When it is a AND, XOR or OR operation in any 8-bit data, or the contents of the register or memory locations can logically have AND operation, OR operation or XOR operation with the contents of the accumulator, and the result is stored in the accumulator. In case of rotate instruction, each bit in the accumulator can be shifted either to the left or to the right to the next position along with carry or without carry. And in case of compare, any 8-bit data or contents of the register or memory location can be compared for the equality or greater than or less than with the contents of the accumulator, and the result is stored in the result is reflected in the status flag. In case of complement, the contents of the accumulators are complemented. 0 is replaced by 1 and 1 is replaced by 0, that is they are toggled. So let us start with this instruction. First instruction is nothing but compare R or compare M. What this instruction will do, it will compare the contents of the accumulator with the contents of the register or memory location. If the contents of accumulator are less than the register or memory contents, in that particular case the carry flag is set. If the contents are equal, in that particular case 0 flag is set. If the contents of A are greater than the register or memory contents, in that case the carry and 0 flags are reset. Okay, so we can use the compare instruction like compare B or compare M. Okay, next instruction is nothing but compare immediate data. So this is same to that of the earlier instruction, but in this case the contents of the accumulator are compared with the immediate data. If accumulator contents are less than the immediate data, carry flag is set. If the contents of the accumulator is equal to the immediate data, in that particular case 0 flag is set. If contents of the accumulator is greater than the immediate data, then the carry and 0 flags are reset. For example, CPI 90H. Next instruction is AND, AR or M. It means it is AN stands for AND, A stands for accumulator. So it will logically AND the register or memory contents with the accumulator. The contents of the accumulator are logically AND with the contents of register or memory. The result is placed in the accumulator. If the operand is the memory location, its address is specified by the contents of HL register pair. Sign flag, 0 flag and parity flag are modified to reflect the results of the operation. Carry is reset and auxiliary carry is set. For example, ANA B or ANA M. Next instruction is ANI and immediate data with the accumulator. This instruction is same as that of the previous. Whatever are the results of the AND operation, it is stored in the accumulator. If it is a and in this particular case also sign 0 and parity are modified, and carry flag is set, auxiliary carry flag is reset and auxiliary carry is set in this particular. Next instruction is ORA R oblique M. It will logically OR the contents of the register or memory location with the ORI 8-bit data. It will logically OR the immediate data with the accumulator, and result will be accumulator. XRA R oblique M. It will logically XOR the contents of the register or memory location with the XRI 8-bit data. It will XOR the immediate data with the contents of the accumulator, and result will be the accumulator. Next instruction is RLC, rotate left without carry. So in this particular case, each binary bit of the accumulator is rotated left by 1 position. Bit D7 is placed in the position of D0 as well as in the carry flag. Carry flag is modified according to the bit D7. So sign, 0, parity and auxiliary carry are not affected in this particular case. For example, RLC. Next instruction is RRC. There is no operand and it will rotate the accumulator bitwise to the right without carry. Each binary bit of the accumulator is rotated right by one position. Bit D0 is placed in the position of D7 as well as the carry flag. Carry flag is modified according to bit D0 and other flags are not affected. Next instruction is RAL. In this particular case, each bit of the accumulator is rotated left by one position through the carry flag. So it is RAL means rotate with carry. Bit D7 is placed in carry flag and carry flag is placed in the least significant position D0. Carry is modified according to bit D7, other flags are not. RAR, rotate accumulator right through carry. Once again, this is the same instruction and carry flag is modified according to bit D0. In this particular case, the binary bit of the accumulator is rotated right by one position through the carry flag and bit D0 is placed in carry flag and carry flag is placed in the most significant position of D7. CMA, it will complement the contents of the accumulator. That is, it will toggle the bits of the accumulator. CMC, it will complement the carry flag. That is, it will toggle the bit of the carry flag. If it is 0, it will convert it to 1. If it is 1, it will convert it to 0. STC, it will set the carry flag. It will set the carry flag. It means the contents of the carry flag after STC will be 1. So these are the summary of the logical instructions. The logical instructions we already seen. They are compare, and, or, XOR and rotate instructions. So these are summarized in front of you. You can quickly go through it before we go for the next category of instructions, which is branching instructions. The branching instructions normally alter the normal sequential flow of the program. That is, our program control will move from one address to the other address. These instructions are generally used when we are using the subroutines or when we are using the program in the form of the loop. So these instructions alter either conditionally or unconditionally. Let us see what different branching instructions. Jump. So this is an unconditional jump. Jump to the given address. For example, jump 2000. So the program sequence is transferred to the memory location specified, that is 2000H, by the 16-bit address given in the operand. The other instructions that are associated with jump are the conditional jump. So it will first check for particular condition and thereafter it will go to the particular address. For example, jump if 0 2000H. So it will check whether the result of the previous instruction is coming out to be 0 or 0 flag is raised or not. If the condition is true, it will jump to this particular memory. So there are various conditional jump instructions. So jump if carry, JC. Thereafter jump if not carry, jump if carry, jump if not carry, jump if positive, that is if sign flag is equal to 0. Jump if minus, that is sign flag is equal to 1. Jump if 0, that is if 0 flag is equal to 1. Jump if not 0, if 0 flag is equal to 0. Jump if parity flag is set. If jump if odd, parity is odd in that particular case, if the parity flag is reset. So jump if even and jump odd, these are the two instructions with the parity. Next branching instruction is a call instruction. The call instruction is basically associated with a subroutine. So there are once again two types of call instructions: conditional call or unconditional call. This is the unconditional call. Call, for example, 2034. So it will call. So basically this instruction, what it does, that the next instruction address which is stored in the stack pointer, it will be stored on the top of the stack and the control will move to the address followed by the call instruction. Thereafter, after execution of the call, if there is a return instruction in that particular case, it will return to the next instruction, that is it will pop off the contents stack pointer to the next instruction of next address of the call instruction. So in this particular way the call is executed. There are some conditional calls as well, so that the call instruction will check whatever is the condition, and if condition is true in that particular case, go to that. So conditional calls are same as that of conditional jumps, that is call if carry, call if no carry, call if positive, call if minus, call if 0, call if no 0, call if parity even, and call if odd. So this call once again will take a call depending on the status of the flags. There are other branching instruction associated with call. It is nothing but a return. So return unconditionally and return conditionally as well. So call instruction will move the control of the program to the subroutine, and from subroutine if you want to return, then we use the return instruction. So there are also conditional return instructions, and these conditions are same as what we have seen before. That is return if carry, return if no carry, return if positive, return if minus, return if 0, return if no 0, return if parity, return if parity is even, and return if it is odd. So in this way instructions are executed. Next sort of branching instruction is nothing but the restart. So RST. So these are RST 0 to 7. And these restart instructions are basically nothing but the software interrupts. For example, RST 3. This software interrupt has a particular vector address. For RST 0, it is 0000H, and from 8 consecutive memory locations, these are for the remaining RSTs. So for RST7, it is nothing but 0038H. Next instructions that we are going to see are the control instructions that perform the control operations of the microprocessor. These are NOP. It will not perform any operation. It will only kill the time of the processor. And this particular instruction is used when you use the delay programs. HLT. It will halt. Most of the time this instruction is written in order to tell that we have completed our program and now we have to do nothing. So it will halt the operation. Other control instructions are disable interrupt. So these are enable interrupt, disable instruction, DI and EI. So enable, these instructions are used whenever we are using the rem and sim instruction that we are going to see. Rem instruction means read interrupt mask. So the rem instruction has a specific format of that particular instruction. Let me read out. Bit D0 stands for interrupt 5.5. Similarly, bit D1 stands for interrupt 6.5. D2 stands for 7.5. And if they are set, then that particular interrupt is masked. I stands for interrupt enable flip-flop. If it is set, in that particular case, the interrupts are enabled. If it is reset, the interrupts are disabled. These are the status of the pending interrupts. And interrupts are pending. These 7.5, 6.5, 5.5, they are pending. If they are pending, then these bits will be 1. And SID stands for the serial input data. So RIM instruction covers both dual purpose, that is nothing but the serial input output, and interrupt controller as well. Okay, so what is the way of using the RIM instruction? We have to first load the bit pattern into the accumulator, and thereafter we have to write the RIM. Similarly, there is a sim instruction, that is set interrupt mask. Bit D0 to D2 will mask the interrupts 5.5 to 7.5 if it is set. Bit D3 stands for mask set enable. If it is equal to 1, in that particular case, it will enable the interrupt mask. Bit D4 will reset the RST 7.5, and bit D5 is reserved. Bit D6 stands for serial data enable. If it is 1, we can enable the serial data. If it is 0, the serial data will be disabled. Bit D7 stands for serial output data. So with this, we have completed all the instruction set of 8085, and thank you for patient hearing. And if you have any questions or doubts, you can contact me personally or you can comment me on blog. Thank you very much. If you found this particular video useful, then you can share and like it.